When it comes to cyclohexanes, the hydrogen in the leaving group we're eliminating in an E2 reaction must also be anti-periplanar. We use a term called transdiaxial, which when it comes to cyclohexanes is the same thing as anti-periplanar. So in other words, the hydrogen and leaving group have to be uh, diaxial and on opposite sides of the molecule for that to be true. So here we have an example of a carbon that has a leaving group, the chlorine, and it has also a hydrogen. There are an adjacent carbons. So if we go this way, we have a carbon that has a hydrogen. And if we go back, uh, we remember this circle represents another carbon that is on the back side. That carbon has a hydrogen. Notice that the chlorine and this hydrogen here are on opposite sides, so they're anti-periplanar to each other, or in other words, trans-diaxial to each other. If we were to rotate this Newman projection, we would see that the chlorine and this hydrogen are also trans-diaxial to each other or anti-periplanar. So this is what it looks like in terms of a chair conformation. The chlorine is trans-diaxial to both of these hydrogens. So a base will come along and could easily remove one of these hydrogens, leading to a double bond there and eliminating this chlorine. Therefore, the E2 reaction would happen very easily. We could do the same thing with base removing this hydrogen and form a double bond there. Now, because of the fact that there's no substituents on this cyclohexane or cyclohexene, um, the double bond being here is the same as the double bond being there. Now, if either the hydrogen or the chlorine are equatorial, then we no longer have a transdiaxial situation. So as an example, this chlorine is equatorial, so it would not participate in an E2 reaction. So this is the chair conformation of that. We have equatorial chlorine. It is no longer transdiaxial to, let's say, this hydrogen here. So if we add a base in this particular chair conformation, we would not be able to do an E2 reaction. Here we have two compounds that show the importance of having transdiaxial groups that are going to participate in the E2 reaction. So first we have neomethyl chloride. So it's this molecule here. Here's the Newman projection. Here's the chair conformation. They're the same thing. We have a chlorine that is axial. And on the back carbon, the adjacent carbon, we have a hydrogen that is also axial. Notice they're transdiaxial. And so if we were to add base, such as sodium ethoxide, the base will come along, remove this hydrogen, and that would lead to forming a double bond there by eliminating the chlorine. So easy peasy, we get an E2 reaction fairly fast with this particular compound. Now, if we were to use methyl chloride, which is the name given to this compound, this is the Newman projection, this is the chair conformation. Methyl chloride has a equatorial chlorine. This chlorine obviously is not axial, so if we look at um, uh, the chair conformation, we would clearly see that as equatorial. So if we were to add base, such as sodium ethoxide, we would not get an elimination reaction. If we want to get any sort of E2 reaction, this chair conformation would have to ring flip to this chair conformation. Remember, every cyclohexane has two chair conformations. So if we have a group like a chlorine that is equatorial in one chair conformation, when we do a ring flip, the other chair conformation would have that group axial. So we see this equatorial hydrogen becomes axial. The other two groups, this one equatorial, this methyl group that is equatorial, would both also become axial. All right, so now we have this very high energy conformation. It is high energy because we have a isopropyl group, a methyl group, a chlorine, all of them in axial positions. You might recall that typically we want groups that are larger than a hydrogen to be equatorial for a more favorable uh, 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 chair conformation. And so this chair conformation with everything being equatorial is more stable than the axial conformation shown here. But this particular chair conformation happens to have a hydrogen and a chlorine that are trans diaxial to each other, which is a requirement for E2. So if we want to get any sort of E2 reaction, we have to go through this high energy conformation where the base can come along, remove this hydrogen, form a double bond there, eliminate the chlorine. We get the product shown here. And then after a ring flip, we turn these two axial methyl and isopropyl groups into equatorial groups. It's the same product, just in a different conformation. Again, these are the two chair conformations of that particular product. The point here is the E2 reaction of methyl chloride is very slow because it has to first ring flip to a very high energy conformation, which then can do the E2 reaction. Compare that to neomethyl, which already has the most stable chair conformation in conformation that has hydrogen and a chlorine that are transaxle to each other. In order to answer this question, we want to first draw the most stable chair conformation for each of these two stereoisomers. So the first one is trans 1-bromo 4-terbutyl cyclohexane. So if we draw a chair conformation, we want to make sure that the terbutyl group, which is a larger group than a bromine, is equatorial. And we can figure out which one is bigger by going at or looking at a table that has diaxial strain values. We would see that a terbutyl group is a bigger group than a bromine. But in this case, it doesn't really matter. The most stable chair conformation that has the terbutyl group and the bromine trans to each other would be this one shown here, where they're both equatorial to each other. Now, the cis isomer, again, would have the terbutyl group and the bromine on opposite carbons of the chair conformation because it's 1-4 substitution. Now, cis means that this terbutyl group is on the same side as this bromine. So we want to put both of them in the same molecule, trans, they're facing opposite sides. Now with the cis stereochemistry, only one of these two groups gets to be equatorial. Again, if we look up the values of diaxial strain, we would find that the terbutyl group is bigger than a bromine. So we want to make sure that that one is equatorial. And then the bromine just is going to have to be in an axial position, even though it's not ideal. It would um, it would be a requirement in order to still have the cis isomer that we want to draw. Now, between these two, which one would react faster? Well, the bromine, notice, is equatorial in the trans isomer. That is not what we want for E2 reaction. So we would want to first convert this chair conformation into the other chair conformation of this compound. That would mean ring flipping it and turning this bromine into an axial position, this terbutyl group into an axial position. So when we add base to it, we can then do the elimination because the bromine is axial. But that required us to go through a less stable chair conformation of this compound, so that's not ideal. In the cis isomer, we already have a bromine that is axial. this hydrogen here is axial. So if a base is added, it will remove this hydrogen, form a double bond there, and eliminate this bromine. So the cis isomer of the cis isomer has the most stable chair conformation already set up to do the E2 reaction. So we can predict that the cis isomer of this compound would react faster in the E2 than the trans isomer shown here.